Hello, everybody. Such enthusiasm before lunch. My name's Scott Allen. I wanted to talk to you a little bit about what I've learned over the last few years trying to build applications that deploy into Microsoft Azure that try to be highly available. They try to be resilient. They try to keep operating even though the seas are stormy and things are failing around them. And I just want to preface all this by saying this is very much, thought I had a picture of money, there we go, a business decision. It's not a technical decision if you want to be highly available or not, because if you're trying to be highly available, you're trying to exceed some SLA numbers from your cloud provider, and as soon as you do that, you can just start hearing the dollars or pounds go by, because you're going to be using more resources. And not only just operational cost is more expensive, you'll also be designing more complex code. Let me fix these slides real quick. They think they're in some sort of a pubconf configuration, so they try to automatically forward, and hopefully that takes care of the situation. All right, rebooting. See if this stays up. And I can give you a good example. Just less than a month ago, or about exactly 1 month ago, I was working with a company, and we're trying to determine how much uptime they need. And I said, given the resources you're using, you'll probably be about 99.9% uptime. And they said, oh, that's horrible. We have to do better than that. And I said, OK, oops, we're still advancing. At 99.9% uptime, your operational cost to run what you need in Azure is about $20,000. And here's an alternate configuration that'll give you better uptime, but it's going to be $60,000 a year to operate. And they said, oh, well, we'll get back to you about this. So it's very much a business decision. And as soon as I get this operational, hopefully it won't advance on me. So we'll talk about how to be highly available, which is somewhat closely related to disaster recovery. You'll see the two have a lot in common, because if you're trying to be highly available, you'll typically have redundant resources available if something fails over. And since you have redundant resources available, like maybe a redundant SQL Server instance, that means if you also need to do some disaster recovery plans, you can factor in these things that are copied all around the globe, your pieces of data that are copied into replicated data structures. So one of the most important things about building a highly available system is to understand the cloud provider that you're working with and the specific features of that cloud provider, or the different resources that they provide that will give you high availability. So if we were to break out the different features inside of Microsoft Azure, I'm not going to list all these, but I usually categorize things as infrastructure services, platform services, or security and management related services. And if you think about, I'm just trying to build a web application, there's a number of different ways I could deploy a web application into these different services. So under infrastructure services, under compute, one way to deploy a web application would be to provision virtual machines inside of Azure or AWS, but we're talking about Azure today. Provision virtual machines, deploy my applications on IaaS or under Linux. And I could also deploy a web application under Microsoft Service Fabric. I could also deploy a web application under an Azure App Service as a web app. So 3 different choices and 3 different implications for how I'm going to architect and design and look at my Azure capabilities, depending on which of these I select. So it's important to understand the different resources in Azure. All of them come with different service level agreements for starters. So one of the first things you do when you're trying to build something that's highly available is trying to understand what is Microsoft's guarantee for availability with a specific resource. So if I choose to deploy to a virtual machine, I would want to Google or search for Azure SLA virtual machines. And that should bring me to this page or directly to the virtual machines page. And on each of these links, and there's one for virtual machines, and there's one for app services, and there's one for SQL Server, Microsoft will describe in very plain English 2 things. They'll first of all describe what the SLA number is, that is, what is the uptime amount that you should expect, and it's measured with a number of 9s, so 99.9% or 99.99%. That's one thing they'll give you. Another piece of information they will give you is under what scenarios that SLA is valid. So for example, if I just go out and provision a virtual machine, one virtual machine in Azure, I should not expect to get an SLA for a single machine. If you read the SLA for virtual machines, what I have to do is provision at least 2 machines and put them into an availability set to get the guaranteed number. So obviously that has an impact on my cost, and it has an impact on how I provision and deploy these things. But the SLA requirements and the SLA numbers for virtual machines would be different than if I deployed my application under App Services. So typically, it's described in a number of 9s. Azure App Services, if I remember correctly, is 3.5 nines, so that's 99.95%. That's 5 minutes of downtime a week or 4 hours a year. Azure SQL Server instances are 99.99, 4 nines, so they'll give you about a minute of downtime a week and 52 minutes of downtime a year. And now I have to look at my application. If my application is running under App Services and it's using Azure SQL Server, it would be reasonable for me to expect that I could have over 5 hours of downtime a year, and Microsoft would still be meeting their SLAs. Because knowing what the SLA is for App Services and SQL Server, these downtime amounts, I have to add them together, because the App Service might be down for 4 hours, and SQL Server might be down for 52 minutes, and those could occur during different time windows, right? So the total the system could be down would be 5 hours, and Microsoft would not owe me any credit. They would still be meeting what they had guaranteed in their SLA. So once you examine the SLAs and see what your expected uptime is, or at least the one that Microsoft tells you you will have, that's when you make the decision. Do I have to beat this number or not? And when you have to beat this number, which is, again, a business decision, but that's when the real engineering comes in, because now you have to figure out how do I do better than this number? And that's kind of what we're going to talk about today. How do I do better than the expected downtime per year or per month or per week? And to do that, one of the things you have to do is, again, understand the capability of each feature that you're using inside of Azure, because each feature, whether it's an app service or SQL Server, has different capabilities when it comes to how do I recover from disaster, how do I stay highly available. So for example, blob storage. Very simple case. I'm writing blobs into blob storage. These are files that my customers upload. I have to have that feature available for my system to be available. And really, Azure and storage, if storage is not available, then everything is kind of hosed. But what does blob storage offer for availability and also, to some extent, disaster recovery? Well, they offer redundant storage. By default, you get what's known as read access geo-redundant storage, which means every time I write a bit into a blob in Azure Storage, that bit will not only be replicated locally within the same data center onto 3 different physical areas of the data center, so it's there even if a single hard drive fails, but it will also be replicated into a different data center in case of the ultimate disaster, which would be the failure of an entire data center or the loss of an entire data center. My data is still somewhere else. And so this replication feature is very easy to enable, and yes, you could pay less by disabling that replication, but if you're trying to be available, if you are paranoid about a disaster, you will leave that read access to your redundant storage replication feature on. If you're using, and those are the different options, locally redundant storage, so it's written 3 times in the same data center. The default, the bottom one, read access geo-redundant storage. We'll talk about the read access part here in just a bit, but that's basically take my bits and asynchronously copy them out of the data center into some other data center, so they are always somewhere on this planet. App services, on the other hand, or virtual machines, on the other hand, if I want to stay available, I know that I have to use availability sets. Availability sets are a way of describing to Azure, look, I have this pool of 5 virtual machines, and I want them to be available as often as possible. So that tells Azure a few things. First of all, it should distribute those virtual machines in a way such that none of them all depend on the same hardware, like a network switch. So if the network switch inside of a rack of server blows up, it shouldn't take all my virtual machines offline. The Azure provisioning system should be smart enough to distribute my virtual machines across several different containers inside that data center so that one physical hardware failure doesn't ruin multiple machines. It also tells Azure look, if Intel has some sort of crazy CPU bug that no one would ever imagine, and we need to update the hypervisor that runs the host system and update the guest systems with new software patches, don't take everything down in my availability set at once. Take just one machine down at a time, update it, bring it back up, and then go to the next one. So that's what availability sets do with virtual machines. You can go into the portal or use scripts to create availability sets, and when you do, you create these things here on the bottom of the slide, or bottom of that dialog, fault domains and update domains. Fault domains are about hardware failures, update domains are about turning things off to reboot for software patches. So given the number of machines that you have, you might change the number of fault domains and update domains you're using. For Azure SQL Server, there's a couple different features. Yes, there's replication. It's really easy for me to go into an Azure SQL instance and say, replicate this database that's running in South UK data center, replicate it to East US or West US or somewhere else on the planet. That's really easy to configure. And SQL Server also, most of the pricing tiers come with a point-in-time restore feature. So it's constantly backing up your database once a day or once every 15 minutes. It just depends on how much you pay. And of course, replication, very different from point-in-time restore. Replication is very good if something fails, hard drive fails, data center goes down, I have that data replicated somewhere else. It doesn't prevent the bug in a program that accidentally truncates a table. That's where the point-in-time restore is useful. So notice blob storage currently has redundancy, but currently there's nothing offered by Azure that has any sort of restore feature. And that's why anyone who's truly paranoid about one of their applications just deleting stuff out of blob storage, there's third-party tools available that you can point to a storage or to a storage account or storage container and say, take everything that's in there and copy it over here, someplace where the program can't access it, right? Because if a rogue program goes in and truncates a table or wipes out all the files in blob storage, that change gets replicated everywhere. So you lose it even if you're replicating. So that's something to think about. So that's an example of the dialogue that comes up when you're trying to choose a replication data center for SQL Server. I can just click on another data center and poof, it ends up over there. And for app services, we have the ability to geo-distribute app services. So I have a web application. It's deployed, let's say, in the South UK data center. But I want to make sure that even if that data center is not available, let's say for my customers in the United States, that I still have something running for them. So I might deploy it in South UK and East US. Now the question is, when my customer comes to my website, scottallen.com or whatever it is, how do I figure out if I should send them to the app service instance that's running in the South UK or the East US? We'll talk about that scenario here before the end of this talk, about how you can do that. So hopefully this is the information you expected. And I'm just going to talk about some of the basic features right now of an app service. We're just going to talk about maybe the architecture of a basic application and what we could do to that application to make it a little more highly available. So let's imagine we have an app service that hosts our web application or our web API. It's something that talks HTTP or HTTPS, and our customers are accessing that with mobile devices, desktops, whatever. The first thing to know about an app service is that every app service has what's known as an app service plan in Azure. And the way to think about the app service plan is think about the plan as describing the virtual machine that you will use to host your app service. So app service plan, really virtual machine. You can put multiple app services on a single app service plan because, again, it's a machine. When you're running a Windows app service plan, you're running basically IIS. You can also choose a Linux app service plan. But just like we can on any Windows server running IIS, I can deploy multiple web applications to that IIS server. I can do the same thing with an app service plan. By default, you get, when you first go in and provision an app service, unless you say otherwise, you get one instance of that app service plan. So there's just one server running your web application. But it's very easy to tell Azure, hey, I need 2 instances or 10 instances. And you will want at least 2 instances if you're trying to be available. And there's auto-scale settings inside of Azure. I'm not going to go into some of those, but it's relatively easy to tell Azure, hey, if CPU percentage goes above 70%, then add another instance, and then wait 5 minutes and reevaluate things, and perhaps add another instance if CPU is still above 70%, or memory percentage, or HTTP queue length. There's a number of ways to do that. So you can scale up and scale down, which is basically changing the number of instances of your app service plan. And I do want to point out before I forget, back at those SLA numbers, when Microsoft tells you that you should expect 99.95% uptime for your app service plan, that means if you do everything correctly. You can't blame Microsoft if you have a deployment process that requires you to restart your app service. Right? Azure does provide deployment slots to make it easy to deploy a new version of my application into a deployment slot and then tell Azure to basically swap slots. So my staging slot becomes my production slot, and I have zero downtime because they will just manage changing around DNS records for me to start sending traffic to my new deployment. When you scale out to multiple instances of your app service plan, Azure automatically puts a load balancer in front. So if one of these instances of that virtual machine goes offline, if it's getting updated, if the hard drive explodes, those sorts of things, there's, at least in this case, still another instance running and ready to respond to requests. So we have multiple instances running. We are using deployment slots, so we have zero downtime. And let's say this application is using blob storage and Azure SQL. So a very simple application setup. We have some redundancy built in already with our app service plan and deployment slots. But basically, what else can we do? And this all might be inside of a resource group, by the way. Well, so a couple, again, looking at the scenario, this is one of those scenarios where I could have basically 5 hours of downtime a year. I'm just using the built-in stuff, multiple instances, but I could still have 4 hours of downtime on my app service and almost an hour on Azure SQL. What do I do? So there's a couple simple things that you can do in software to sometimes improve your uptime numbers, and one is as simple as connection resiliency. So there's always in the cloud transient faults happening. In fact, I don't know if anyone has tried to use Azure SQL or tried to use Azure SQL back in some of the early releases of Azure SQL, but it was always having these transient faults from ADO.NET connections where the ADO connection would just fail, and you try again a little bit later and it would work, but the transient faults were very disturbing to people because in the old days, we didn't write our programs with connection resiliency. We just tried to attempt a SQL server, and if it failed, well, that thread is over. We stop. We throw an exception. It's all over. Connection resiliency is simply, OK, it failed. Let me wait a little bit, try again. Let me wait a little bit, try again. Hopefully, that'll go through. And this can happen not just because SQL Server is down, by the way. This can happen because maybe you under-provision SQL Server. So you need to watch out for that, too. When you assign an Azure SQL instance, you need to select the number of data throughput units it uses, which is basically how powerful do I want my SQL instance to be. The more powerful, the more I pay. But if I don't have it configured to be powerful enough, it can simply start to ignore some of the work that you try to ask it to do, and it'll fail those operations. And so connection resiliency actually is quite easy to do for a lot of scenarios, because if you're using the official Azure SDKs, a lot of them already have this retry logic, this resiliency built in. So for Azure Storage example, if I want to talk to blob storage or a queue inside of my storage account or table storage, there's retry logic in the official C# NuGet package, in the official JavaScript NPM package. There's nothing I have to do, although I could configure it a little bit. So this would be an example in C# code of saying, I want to connect to my storage account. Here's the connection string. Now I'm going to create what's called a blob client to be able to talk to blob storage specifically. And any request that I make with this client, here's some default options. First of all, location mode, I want primary, then secondary. In other words, if I try to connect to my primary instance of blob storage to read a blob or write a blob, and it's down, well, this would actually only apply to read scenarios. If I try to read a blob and it's not available, go to my secondary storage location where things have been replicated and read it from there. But you can also retry. So keep retrying that primary using a linear retry of 500 milliseconds. So wait 500 milliseconds, retry again. Wait 500 milliseconds, retry again. The default is an exponential backoff where it keeps increasing the time between the retry attempts. And the maximum number of attempts is 3. So that would be a way, if I want low-level control of my resiliency, I could do that. For Azure SQL, there's nothing in the official SDK because SQL is a little bit different. You can talk to it through various protocols. But if you're using the Entity Framework, there's an option, both in Entity Framework 6 or 7 or whatever that last version was, and Entity Framework Core, to say SQL options enable retry on failure. So that'll work through those transient connection attempts. And all these retry logics, I should point out, are smart. They're not going to retry operations that are obviously going to fail. So for example, with enable retry on failure with Azure SQL, if I try to, let's say, insert an object through the Entity Framework that's going to generate a foreign key violation or a primary key violation, Entity Framework's not going to retry that. It makes no sense to retry that operation. It's always going to fail if I'm missing some valid database constraint. But it's smart enough to listen for connections that are exceptions and error codes that might happen because the network's not available, or the host is not available, or SQL Server's too busy at the moment. It understands that, yes, I could retry that operation, and maybe it'll work in 500 milliseconds or 3 seconds from now. The other thing, before I leave here, before I leave retry logic to point out, is that sometimes retries make the situation worse. It's really interesting how systems behave under load, and that's why I always suggest people try to load test and try to generate some forced error conditions to understand how your application behaves. But if a server, let's say your front-end web application is calling a back-end API service over HTTP, and something's wrong, you have this retry logic, well, maybe that back-end service is just under load. The CPU is pegged, the memory is exhausted on that virtual machine, and now you have this retry logic that just keeps sending more requests. It doesn't help. Sometimes you just need to stop and say, well, we're going to give that thing 5 minutes and see if it recovers. Maybe it has to reboot. I don't know what's going on with it. And that's when simple retry logic doesn't work. That's when you might try something known as the circuit breaker pattern. So I'll show you a library that can help with this in just a moment, but let me describe it. The circuit breaker is a stateful component that wraps your interactions with some other service. And the circuit breaker, like an electrical circuit breaker, by default is going to be closed, so electricity, in other words, messages, can flow between these two systems. But it's stateful, so it's keeping track of things like, oh, I see you've made 10 successful requests over the last second. Good, I'll keep the connection closed, or the circuit closed. But maybe you've programmed the circuit breaker to say, I've seen 10 failures over the last second. Something must be wrong. Let me pop open the circuit. And now, instead of your retry operations hammering the service, the circuit breaker makes them fail fast and just immediately says, no, this connection's currently shut down. We're going to maybe retry it later, but for right now, we're not going to send any more requests to that server because it's failed so much over the last second or 30 seconds, what have you. And then at some point, you can program the circuit breaker to go half open, which doesn't really work well with electricity, but in the half open space, it'll start to allow some things to trickle through. So maybe it'll select 1 out of 10 of the next connections and allow it to go through. That's kind of a test. Is the backend service responding now? And if things look like they're working, it'll close again. Things are back to normal. And maybe that gave that backend server a chance to reboot or patch or clear out some HTTP queue that was building up. And now the system's back to normal. So how would you implement something like that? It obviously sounds non-trivial. Anyone use poly.net? Heard of it? Oh, good, yeah. So awesome library to encapsulate policies about what you want to happen when something's not working. So if I get an exception, do I want to retry it? If I get an exception, do I want to use a circuit breaker to shut things down and fail fast? And the documentation is quite good. Just to give you a simple example of the API. Yeah, I mean, it's like a Fluent API. So I want to build a policy that will handle divide by 0 exceptions. I'm going to retry it 3 times, which chances are you'll still divide by 0, but hopefully you can see that you could look for particular types of exceptions that represent transient faults. The network not available faults, host not available faults, server too busy type of faults. And those are the type of operations that you might want to retry. And this handles, apologies for making anyone nauseous if I'm scrolling, you can build retry policies, circuit breaker policies, timeout policies, excuse me, I need a drink, bulkhead isolation policies, which can be quite useful. This is like on a ship, when you have a bulkhead, one of the things it does, if someone punctures a hole in the side of the ship, it prevents the water from spreading throughout the ship. It just floods one area. Likewise, in software development, sometimes we have these components, like a good example in .NET is the whole HTTP client issue. I don't know if you know the HTTP client issue drama. I could probably spend an hour talking about HTTP client, but the suggested use of HTTP client is as a singleton. But anytime you get into using a singleton, so I'm going to use one object to connect to all my services, HTTP client, that can become an issue if something is inherently wrong with that HTTP client. Maybe this one service over here puts it in a bad state. Bulkhead isolation would be about, okay, we're going to use this client, and it's isolated this HTTP client to talk to this service or this collection of services, and that's in a bulkhead separate from this other one over here. So caching policies, fallback policies, and then policy wrap is a way to say, hey, take my circuit breaker and my retry and this other thing and wrap them all up into a bigger policy. So pretty cool library called Poly. If you just search on whatever search engine for GitHub poly.net, I'm pretty sure you'll find this repository and you can read through the documentation. All right, so moving on. Graceful degradation, another feature to consider. So my app service talks to SQL Server. What happens if my SQL Server is not available? It's experiencing one of those downtime moments. What can I do? Well, for reads, maybe, just maybe, I could go to some other data source that might be available and read some data that was cached, maybe 5 minutes ago or half an hour ago. And of course, this depends on your application. If you're building an application that provides customers with stock quotes or Bitcoin quotes, then you can't give them 5-minute-old information, right? That could ruin somebody. But if you're someone who's an e-commerce vendor and you just can't get to the inventory service to determine if you have enough widgets for this order, well, maybe it's okay if you read what was there 5 minutes ago and tell the customer, hey, we still have 10. Because if you don't have enough, you could always send them an email afterwards and just tell them their shipment will be late. It works for some industries, right? It doesn't work everywhere. What if SQL Server is not available and I need to write something into it? Well, maybe if I have a backup that's a message queue and the message queue is still available, I could write that command that describes what information I need to place in the database or how I'm manipulating the state of my application. I could place that into a message queue instead of directly into the database. And one of the things you'll realize here is that reads are separate from writes. And if you've heard of the CQRS strategy, CQRS design pattern, that can be a very effective pattern to use for both scalability and reliability of an application. So there's been many talks over the years at NDC about CQRS, I'm sure. So you can look those up. But it's basically about separating reads from writes. So just having a different path through your code for those two different operations. But this is easier said than done, right? This is where not only do I pay more operational costs for running SQL and Redis or a second instance of SQL or something for that second data source and some queues, not only am I paying more operationally, but now my code is much more complex. And that's sometimes a more important factor. Now, when someone gives me a report that, hey, such and such a customer experienced this issue on the website, then I have to say, okay, well, I wonder if that was reading from the database or if the database was down at that time and I was reading from somewhere else. You know, it complicates things. Complicates not just the code, but also debugging issues and figuring out what's happening inside of your environment. So you, again, really, really, really want to beat the Microsoft-provided SLA numbers to introduce some of these more advanced architectures. What about this? What if we wanted to build an application with an app service that is using this queue, that is using blob storage, that is using a Redis cache, that is using Azure SQL, slightly more sophisticated application. But here's what I want to do. I want to take this application, now that I've made it more redundant, and I want to deploy it in multiple places. So I want to deploy it into 2 different data centers, one in South UK, one in East US. Now, even if East US is down, I can send all my customer traffic to the one in South UK. How do I do that? That's where you can use an Azure load balancer named Traffic Manager. So there's 3 different types of load balancers in Azure. Let me talk about Traffic Manager first. Traffic Manager is a DNS-based load balancer, meaning you will go in and you will configure Traffic Manager to respond to DNS queries from your customers. So when they go into the browser and type in scottisland.com, and the operating system goes off and says, hey, what IP address is scottisland.com, that request will go to Traffic Manager, and then you program Traffic Manager to know about your different deployments. So you say, hey, I have this app service here, I have this app service here. It knows those 2 different IP addresses. And you tell Traffic Manager, there's several different ways to program it. One way to program Traffic Manager is to say, actually, I think we have time to just create one real quick. I'm not sure if I have any screenshots for it. I hate talking about things in the abstract, but shouldn't take too long. I'm not going to enter passwords and all that. I'll just talk about it. I can tell Traffic Manager, respond using performance-based rules. So Traffic Manager will determine which of those 2 IP addresses to hand out based on the customer's location and what the expected latency is between that customer and that particular data center. So a customer in East US will probably get routed to the app service instance that's also in the East US, unless that app service is down. Because, by the way, Traffic Manager is also doing health probes. Once I tell it about these 2 different app services, it's constantly sending HTTP requests to an endpoint that you provide. So you could build something in your app service like /healthcheck and tell Traffic Manager, go to /healthcheck. And if it goes to /healthcheck and receives a 200 response, it says, OK, you must be good. But if it returns anything other than a 200, even like a 301, which isn't really an error code, but if you return anything but a 200, Traffic Manager says, I think something's wrong over there. I'm going to stop sending traffic. But it'll keep checking to see if it recovers. Anyway, so you can tell Traffic Manager to route users based on performance, which is interesting. You can also tell Traffic Manager to route based on geography, which is interesting for geofencing. So if you need your EU customers to be routed to a data center that is also in the EU, and US customers stay in the US and so forth, you can do that. You can also tell Traffic Manager to do priority-based routing. So you can say, send 90% of my traffic to the first app service and send 10% of my traffic to the second app service. And sometimes that feature is useful for things like A/B testing. So I have one app service where I've deployed my new features. I can tell Traffic Manager, send 3% of my traffic there, because I'm just doing a test to make sure nothing explodes in spectacular fashion. And after that runs for maybe 8 hours, then I'll also deploy that into the other app service and, hey, change the Traffic Manager rules to just balance between the 2. And you can have nested Traffic Manager profiles, by the way. So I could have Traffic Manager that routes a user to another Traffic Manager because they live in the US, and this other Traffic Manager routes based on performance or priority, what have you. So in the portal, it's real easy to say, create new Traffic Manager. You can also do it with a script, of course. You tell it about your different deployments, your different app services, and just tell it how you want to be route between those. Yeah, so Traffic Manager is one of 3 load balancers. And I just want to point out, because sometimes people get confused about this, but Azure Traffic Manager is sort of the highest level network load balancer. It's a DNS-based load balancer. You configure the DNS timeout there. The default, I think, is 5 minutes, 300 seconds, which means every 5 minutes, your client should re-query whatever DNS server to say, hey, what was that IP address for scottisland.com again? Which means if your app service fails, your customer could be looking at blank screens or errors for 4 minutes and 59 seconds until something triggers another DNS query. So you could go into Azure Traffic Manager and set the time to live, the TTL, to like 30 seconds. But then you have the overhead of now your client is making a lot of DNS queries all the time, trying to find out where to go. So Traffic Manager, DNS-based load balancer. The lowest level over here on the left, the Azure Load Balancer. That's a network layer 4 load balancer, meaning it operates at the TCP IP level, meaning you typically don't put this in front of web applications. You typically put this in front of virtual machines that are doing socket-based protocols like RDP or stuff like that. So for most web developers, the Azure load balancer isn't interesting. And so what's confusing is, what do you use as a web developer? You use the Azure Application Gateway. That's a layer 7 load balancer, so it operates at the application level of the networking stack, which means it understands protocols like HTTP and HTTPS natively. So you can use this Azure Application Gateway in front of your web application, which I'm going to come back. I have to remember to give you the caveat there. You can use this load balancer in front of your web application to do things like inspect HTTP headers. There's a firewall with it, so you can control traffic a little more tightly. You can have it set affinity cookies if you need them. So if you need a customer, when they come to you with their browser or their service, if you need their request to always come back to the same server, that application gateway can set an affinity cookie to make sure they arrive at the right spot. And the thing to be aware of with Azure Application Gateway is, yes, you can place it in front of a web application that's deployed on virtual machines. So if you're using pure virtual machines, maybe putting containers on those machines, that's where you would configure Azure Application Gateway. I don't need to put this in front of an app service. My app service already has basically an application gateway. It's just one that I don't control. And so a lot of people say, hey, there's certain features of Azure Application Gateway that I like. How can I use that with an app service? And the answer today would be, the only way to do that is to create what's known in Azure as an isolated app service. And it's actually in the list of pricing plans for app services now. But the thing to be aware of with the isolated environment is tremendously more expensive, because the word isolated basically means what Microsoft is doing for you is not just putting you in the regular app service environment. They're creating a whole special app service environment for you and giving you a set of virtual machines to run that environment. But because they're giving you a set of virtual machines, it gives you a little more control over your environment, your app service environment. A little bit of a tangent here, I guess, but people come to me and say, hey, my app service has, by default, a public IP address. How do I get rid of that? And the answer is, well, you don't with an app service unless you get an isolated app service. Because then you can put you can put it behind a gateway, you can put it behind virtual networks, you can do all these other interesting things. The big one that gets some people is when you have a regular app service, just know that a secure connection to that app service gets terminated before it reaches your app service. So there's another network appliance or piece of machinery inside of Microsoft's data center that takes that SSL connection and decrypts it, and then forwards HTTP traffic to your app service, which disturbs a lot of people because it means there's some unencrypted stuff going back and forth in the data center. Right now, the only way to get true end-to-end SSL encryption would be to use either the isolated app service, because then you can configure this application gateway to terminate SSL and still forward a encrypted connection to your app service, or to use virtual machines. Anyway, moving on. Hopefully that all made sense. I'm just, I get in a rambling mood when I'm jet lagged. So 3 different load balancers, that's how you'd use them. This was just describing Traffic Manager in a little more detail, so I'm going to skip over with that, but it was just, this Traffic Manager was configured to use priorities. The one I described to you earlier was not priority-based routing. The one I described to you is what they call weighted routing. Weighted routing is where you say 97% traffic here, 3% traffic there. Priority routing is basically, here's my primary endpoint, my secondary endpoint, my third endpoint. And Traffic Manager will just start falling back to the other app services or resources that you've registered if one goes down. And I should point out that Traffic Manager is not just app services. Inside a Traffic Manager, I can point it to an app service. I can point it to a web application on a virtual machine. I can point it to a web endpoint that's running in AWS, or an endpoint that's hosted in my own data center, something that has a public IP. So it's not just restricted to Azure stuff. It's basically a way to get a DNS load balancer that works everywhere. This was an example showing 2 instances of the same app service, just one running in East US, one running in West EU. And I did have some screenshots. So after I create Traffic Manager, this is where I could go in and set the routing method: performance, weighted, priority, geographic. And yes, this would be sort of the default name, like musicstore.trafficmanager.net, but of course you can purchase custom domains to assign to that, because you'll have an IP associated with that Traffic Manager profile. And then, yes, of course, you can purchase SSL certificates so that HTTPS traffic arrives there to your custom domain name. And this was where you could say, yes, for this Traffic Manager, I want the performance routing method with a 300-second time to live on the DNS responses. And then this is where I'd add my endpoints in. Say, here's my first deployment, here's my second deployment. All right, load leveling, something else to think about. It's very easy for front-end services to receive messages from customers that have to kick off back-end services that need to do a lot of heavy lifting. And that becomes a problem when you have a lot of customers arrive, let's say at 9 a.m. on a Monday morning, or when some activity happens in the news, and all these people are creating operations that are overwhelming your backend because there's just so many requests. The web server can handle it, the backend cannot. That's one of the biggest struggles sometimes in distributed systems, is just trying to get things to work together all at the same capacity. So that is where I would make sure to introduce, again, message queues, have some ability to place messages into a queue from the web front end, so that when the traffic spikes like this, the front end will just place a message on the queue that says, hey, we need to do this work. We need to batch update this thing. We need to place this ticket reservation. And the backend service, however you provision it, can just pull messages off of that queue as it can to process those things. And it might need to take half an hour to work through all the messages during a rush. But that's OK. It was better than that service being overwhelmed and shutting down when all the customers arrived at once. We've used Azure Service Bus over the last couple of years, and it's been very effective at a number of things. Azure Service Bus has all sorts of nice features in it about message deduplication and the ability to schedule messages in the future. So I could say, drop this message in the queue, but not until 11 a.m. tomorrow morning. That type of thing is kind of nice. It has queues, so simple queues that you can use to decouple two services. So typically you use the queue when service A wants to tell some other service to do something. So it puts a command in that queue to tell some other service to do it. It doesn't know what service will do it, but one other service will pick up that message and do something, which is different than topics, where I can place a message in a queue, and there can be multiple listeners on that topic. So I might place a message on the queue that, hey, customer Scott Allen just placed an order for an umbrella or a wind jacket, or I guess I need a heavy jacket this week here. Really was hoping it would be a little warmer weather. Anyway, that message that gets dropped in a topic could be handled by a few different services out there. They can all subscribe and listen for things that will, one might be the email alerts, one might be the inventory management. Different services can work on that particular command. And then relays and Service Bus in general have been very effective for us, because we deploy a lot of custom software over the years behind company firewalls, just for historical purposes. We're slowly moving stuff into the cloud, but even in the cloud, we still need something deployed at the customer site to be able to load data. And Azure Service Bus has the nice feature of you can open up a Service Bus listener behind a firewall and still be able to effectively communicate with it, because I can drop a message in a queue, and it shows up inside the firewall and is processed by a piece of software running at the customer site. So it's kind of quite useful. And Azure Service Bus, pretty easy to use, just trying to make things a little more concrete so you can see what the code is like if you haven't worked with Service Bus. But typically your connection string would look something like, I've created a service bus called psmessaging.servicebus.windows.net. That would be my namespace. So I have a connection string here that would include some sort of access token in that connection string. So I'm going to create a queue client. I'm going to put together a message body that is a simple string. You can put together messages that are populated with XML or JSON, whatever floats your boat. Create a new instance of a brokered message where I will give that message body to, and then just tell the client to send it off. And poof, someone else can read it. And the read operation is pretty straightforward too. I would create a client and listen for messages on a particular queue. Load throttling is something you might also want to consider depending on the type of application you have. But let's say you are building an API and you expect customers to be able to sign up and use your API. Maybe they're paying money for your API, maybe they're not. But you can always get that one customer, as soon as you give someone a programmatic API, someone can abuse it. So someone, even accidentally, might write a for loop that just hammers your application service making API calls. You want to prevent that. You could write that in your code inside of your application, or you could put some sort of API gateway or API manager in front of your app service. So there's a number of these API gateways. Some of them are open source, so you can certainly consider them. Azure's version of an API gateway is a tool called API Manager. And effectively, it works as a proxy that sits in front of your APIs, which could be spread across multiple things. So there's a number of interesting use cases for API Manager. One is this. Let's say I have an app service that I want to monetize, and I just want to make sure it doesn't get abused. One easy way to do that, if I don't want to write the code myself, is to create an API Manager in Azure, tell it about my app service, the address that it's at, and now my customers will connect to API Manager instead of directly to my app service. And when they connect to my API Manager, it can do these things like implement throttling rules that you give it. So it's very easy to go into API Manager and say, hey, for any particular customer, we're not going to allow more than 5 calls a second or 5,000 calls a week. And you can also build a single API endpoint or name space that your customers go to and have those messages forward across different microservices that are spread all across different things on your back end and built by different teams. So for example, someone comes to scottisland.com/API/widgets. API Manager might route that to this app service, which is on a completely different name. And if someone comes to scottisland.com/API/invoices, maybe that comes over here and it's implemented with Azure Functions or something. So it's a nice way to coalesce these things together too. API Manager can consume metadata about your APIs if it's available, which allows the traffic API Manager here in the middle, it allows it to understand your APIs and allows it to export documentation to the developers who are signing up to use your APIs. So if you can produce a WADL document or a WSDL document or a Swagger document and give that to API Manager, it knows about all the operations that are inside of your service. So this is setting up an API Manager. You'll notice there is a cost associated with it. It's not trivial, but hopefully you'll be able to monetize APIs and be able to make this money back. It has once you set it up, it gives you a developer portal where you can go in and manage your APIs. It also gives you a public portal where you can send your customers and their developers. You can send them here and they can sign up and register for a key and browse your APIs and browse your documentation. So it's quite a useful tool, just going through some of the screenshots of it. You can divide your APIs up into different products, apply policies. This is where I would apply throttling policies. You'll notice this list of policy statements on the right. Those are just some built-in policies that I can drag and drop over. So if someone in my organization wrote an API, but they didn't have CORS headers set in there, if I put it behind an API Manager, I can add those CORS headers for them without them changing code. So that'll be the CORS headers down here. Yes, that was a topic I didn't quite want to talk about. I just wanted to end the talk with a couple of topics here. If you go down this road of trying to be highly available, trying to do disaster recovery, you have to automate everything that you can. You cannot go and ask someone in your IT department or your developers to say, hey, stand up a new instance of our application in the East US data center because we're going to deploy there now. That has to be a script that's checked in somewhere that someone just executes. It's been parameterized, so you just pick the perhaps data center and the names that you want for that particular installation. Sometimes it's difficult to maintain those scripts and create those scripts, but the net benefit pays off in many ways over time. And you have to test. You have to test. You have to make sure not just the traffic manager, let's say, is configured correctly and working for you, but the more you set up these complex systems that involve traffic manager and 2 app services instances and geo-replication, and this thing will read from Redis when it can, and it will read from a SQL database if it can't, you have to test out those scenarios just to see how your application is going to behave when things go wrong. Because you don't want to be debugging things in a panic mode when something actually goes wrong. It's always very nice when someone presents you with an error from the application or a log from some part of the application where you say, oh yeah, we saw that last week when we were trying things out, and we know that's when Redis goes down, that sort of thing. So test and introduce failures and take that Netflix chaos monkey approach of having something that goes out and forces services to be in a faulted state. Turn things off, disable things, see how the application behaves when something's turned off. Is valuable understanding how things will behave, and of course monitor everything. The built-in Azure monitoring tools are okay, but you have to spend some time with them to make sure you properly configure the alerts and you're getting the right metrics. A lot of people use some third-party tools, which is cool too. And with that, I'll just say, yeah, I have Pluralsight courses, but if you have any questions, feel free to email me. Otherwise, thank you for listening to me on this topic, and I hope you enjoy lunch and the rest of the conference.